Okay, let's begin. So continuing with the handout from last time with group work. So we are on problem 5, which group 4 did. Okay, area inside one leaf of this. Okay, who was group 4? Okay, what'd you do?
We started off with the R theta graph. So we knew that our A was 3, B is 0, C is 0, and then our period is 2 pi over 3. And then the graph is over intervals that go into 4.
Which is pi over 6.
Yeah.
So go down, boom, 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 boom. Theta versus R. We go up and down by 3. From the center point of 0. This is 2 pi here. 2 pi over 3 is 1 period. So something like that. Split each of those into 4. And you want a positive cosine graph. So here, it's the middle, it's the bottom, it's the middle, it's the top. It's the middle, it's the top. It's the middle, it's the top. So that's our graph. Okay. So that should be able to do relatively quickly. Each of these pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. So from that, we can draw the R theta graph. So what do we need here?
Circle of radius 3.
Okay. If you look at the guys on the y-axis, those tell you what the radii that you want. There's only one of concern here, so circle radius 3. This is the x, this is the y, and what did you do with this circle?
Well, we also have to get the angles for
Mhm.
the pi over 6.
So pi over 6 just means you divide pi into 6 equal pieces, so that means you divide each quarter into 3 equal pieces. So this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 0, which is equivalent to 12 pi over 6. Okay, where do you start here?
Radius, circle radius 3 at 0.
Okay.
And you go to 0 at angle pi over 6.
To the origin.
And then you go to opposite of pi over 3, so for pi over 3 at circle radius 3. And then back to the origin. And then to 2 pi over 3 at the circle. and then back to origin, and then back to the starting point. So it's negative pi, which is just 2 pi so 33, and then it just repeats that again.
And it actually just goes over and retraces that. Okay, so that's your polar graph. You want to find the area of one of these leaves, the implication meaning these are symmetric. So you care about this. Okay, how'd you go about finding that?
Well, that particular one, so basically we just know that it will be in between the 2 zeros. One of the leaves will be in between 2 zeros on the graph. So you can, for that one, that would be after we get to pi, so it would be between 7 pi over 6 and 4 pi over 3, that particular one.
So which one did you guys do? Or do you remember?
I think I did the second one, so I did the one between pi over 6 and pi over 2.
The one between pi over 6 and pi over 2? Oh, so you looked at this?
Yeah. But I mean, like, I still found the area.
Yeah, okay, so that's gonna be this one then you're looking at.
That's actually the bottom one.
Because, where are we? It was over here.
Yeah. Doesn't
Okay.
matter, you can.
It doesn't actually
Yeah.
matter, but let's get to the one we want here. So this one, at pi over 3 it's negative, so we actually want the opposite, so you actually found this one.
Yeah.
Okay. And so how did you actually do that?
You know, the area is gonna be the integral from, considering the green one, then pi over 6 to pi over 2.
And that is, in fact, you could actually just look at this. You know that a leaf is formed when you start at the origin, you go away from the origin and you come back.
Yeah.
So you can just find the area a part of any one of these guys. So you could integrate from pi over 6 to pi over 2, or pi over 2 to 5 pi over 6, or 5 pi over 6 to 7 pi over 6, etc. A word of caution here, you need to make sure that, warning, I don't know, maybe that should be in red, I don't know. You always kind of integrate in increasing angles. Integral must have increasing angles here. So, for example, if you wanted to do this leaf, integrating from 11 pi over 6 to pi over 6 would not be what you want to do, because that will actually go from a larger angle to a smaller angle. What you could do here is you'd have to think of this as moving backwards, so 11 pi over 6 is equivalent to minus pi over 6. You'd integrate from minus pi over 6 to pi over 6. So if you're going from a point below 2 pi to a point above 2 pi, you have to be aware that you want to go in increasing angles, so you might have to find a reference angle for the angle that you care about. So you do want to make sure that these guys are actually in increasing order. Okay, that being said, what's the formula?
1/2 r squared.
1/2 r squared d theta. So your r is just going to be that guy, so we're going to square that. So it's 1/2 times integral from pi over 6 to pi over 2. By the way, a nice one would also be to integrate from 0 to pi over 6 and then double it. So 0 is nicer to plug in, but let's continue here. We're going to square that, that's 9 times cosine squared 3 theta d theta. How did you do with that?
Take the 9 out and then you can do what was it? Yeah, Pythagorean here, so 1 minus cosine, or 1 minus sine squared d theta. And then you can, oh wait, no, I guess you could just go straight to the double angle thing.
Double angle? Okay, so what would that look like?
Is it one, it's 1/2 1 plus cosine 2, so it'd be 6 theta?
Cosine 6 theta, d theta, and we can bring out the 1/2 out here, make that a quarter. So you want to integrate that. Now, this part here is actually gonna go to 0 because the period of this is actually pi over 3, and we are integrating over a length of pi over 3. So you can actually know that this was going to go to 0. But of course, it's not gonna be too much trouble to actually integrate that and get 1/6 sine of 6 pi 6 theta. Then when you plug this in, you get sine of 3 theta, which is 0. Plug this in, you get sine of pi, which is 0, 3 pi, which is 0, and sine of pi, which is 0 respectively. But other than that, you integrate this, you get just theta, 9 over 4 theta between pi over 2 and pi over 6. So that's 9 over 4 times pi over 2 minus pi over 6. So that's 3 pi over 6 minus pi over 6 is 2 pi over 6, which is pi over 3. So it's 9 over 4 times pi over 3. So it's 3 pi over 4. Was that what you got?
Yep.
So that was the area here. This brings us to problem 6 / group 5. Any questions on anything that happened here? It's very similar to the previous problem that we did at the end of the last class. Problem 6 though is a little bit different because you have 2 curves to consider. So where's group 6?
Yeah.
Yeah. Julia skipped out on you guys.
Yeah. She left us hanging.
So, problem 6 is group 5. So we want the area inside the r equals 2 plus 2 cosine, but outside r equals 3. Okay, so what did you do here?
So, A equals 2.
I assume you're doing this
So
one?
we start with that. So A equals 2, B equals 0, C equals 2, and our period is 2 pi. And then pi over 2 is.
So period over 4 is going to be pi over 2. So we're going to go home. This theta, this is r. RC is going to be 2. And we go up by 2 to 4. We go down by 2 to 0. And we just have a regular 0 to 2 pi graph. It's in 4 sections. And we have a cosine, regular positive cosine. So it's this, it's the middle, it's the bottom, it's the middle, it's the top. That's our graph here. Okay. And what did you do with that?
So we made the graph, and we made a circle of 4 and 2.
Circle of radius 2, circle of radius 4.
And then we did 3 after. We sketched it first.
Okay.
So then we start at
You did 3 after?
like we drew in the third circle of radius 3 after.
Right, so r equals 3 just means a circle of radius 3, which means your r is always at this part here.
Right.
Which means that's just the graph of that is literally just a circle of radius 3. So there's 3 here, that just goes in. Okay.
So then we start at 0 when we start at r equals 4 when we're at theta equals 0.
Let's put in these angles here. So this angle is 0, which is equivalent to 2 pi. Then we'll have the pi over 2, the pi, the 3 pi over 2, and the 2 pi. Okay.
So then we go to radius 2 at pi over 2. And then we go to 0 at pi. So just 0.
So this is pi over 2 pi, 3 pi over 2, 2 pi.
And then we go to radius 2 at 3 pi over 2. And then back to radius 4 at 2 pi over 0.
Alright, where do you want?
So we have to find between pi over 2 to 3 pi over 2.
Come again?
Um,
You want to be outside the circle, but inside that cardioid it's called.
Right, so we did, so first like the equation was 1/2 3 squared minus r squared d theta.
Yeah, but what region on
The
this
bounds
picture?
first, we did from pi over 2 to 3 pi over 2. I think. I forgot, because I gave in my work and Julia was the other one that did this problem and she's not here, so.
Yeah. Well, just let's do it now. What's the shaded region that we want here?
Is it the like the tip of the heart on the right side?
Yeah,
Care about this part here. Right, which means we now also care about the angle that intersects them. How do I find that angle?
You plug in radius 3 into, so 3 is equal to 2 plus 2 cosine theta.
yeah.
3 is equal to 2 plus 2 cosine theta. This would mean that 1 is equal to 2 cosine theta. This is cosine theta equals 1/2, so your theta would be?
60. Is it 60 degrees?
Pi over 3,
Yeah.
and? Because clearly there are two intersections here, right? This graph intersects here. That first one is pi over 3. What's this one?
It's 11 pi over 2. No, I can't do that.
It's definitely a reference
negative
angle
pi
for pi
over
over 3.
3.
Huh?
Is it negative pi over 3? Negative pi over 6.
Well, on this graph, negative pi over 3 would be over here. What's the one here?
5
5 pi over 3. Right? Remember, pi over 3 just means you divide pi into 3 pieces. And you know that all students take crack, I mean calculus. And then what happens is you want, so the cosine is positive in these two quadrants, which means you want this reference angle, and you want that reference angle. So that's 1 pi over 3, which is the first one, and then 1, 2, 3, 4, 5 pi over 3, which is the second one. So this here is 5 pi over 3. This here is pi over 3. Now, yes, if you're integrating from here to here, you would think of this as minus pi over 3 to actually put in the integral, because you definitely want the angles increasing. This is symmetric though, despite appearances, so you could also do 0 to pi over 3 and then double the answer. But ultimately, we want the area between two curves, and we have the formula is, what's the formula for the area between two curves?
1/2 r from theta 1 to theta 2 r, I forgot the,
Huh? Big R squared
big R squared minus little r
minus little r squared.
Yeah.
Right, where this is the outer radius and that's the inner radius. Now if you're here, the outer radius measures to the cardioid. So that's going to be 1/2 times integral of, all the way out here is that guy, so that's going to be the 2 plus 2 cosine theta squared minus, to measure the inner radius, the one that's closer to the origin, is just 3. So that's the integral we want. And what are the limits?
From pi over 3 to 5 pi over 3?
Well, no, because that would tell you all of that.
But I thought you said, because
Right, if you're opening from pi over 3 to 5 pi over 3, you go that way. You literally get the errors on
Of the
this side.
opposite side, yeah. So it would be 5 pi over 3 to pi over 3.
Negative pi over 3 to pi over 3?
It's negative pi over 3 to pi over 3.
Or could you do 0 to pi over 3 and then just cancel out with the half?
Mhm. You could also double it from 0 to pi over 3, and that would also work, which is probably nicer. Let's write this as then just 0 to pi over 3, and I'd expand this. This is 4 plus 8 cosine theta plus 4 cosine squared theta minus 9. And so that will be from 0 to pi over 3, 8 cosine theta plus 2 plus 2 cosine 2 theta minus 5. Or in other words, I can combine this with that, and so minus 3. Another way you could, I erased it, but another way you could have seen the angles, you can actually figure it out from this graph right here. Is notice that we kind of want where this line and that what's bounded between the line, what's above the line but below the trig function. Because I want what's outside the circle, so it's larger than the circle, it's a farther distance from the circle, but it's smaller than the trig function. So you could actually see that I could integrate from 0 to 3 pi over 3 and then double the answer to get that one. Or if you continued this graph on the other side, you'd realize that you would want to integrate from minus pi over 3 to pi over 3. So you can actually use this graph to figure out the angles as well, but you would of course have to compute them here. Let's finish. So integrate 8 cosine theta, that's 8 sine theta. And 2 cosine 2 theta, that is sine 2 theta. And minus 3 theta. Sine pi over 3 plus sine 2 pi over 3 minus pi minus 0. Sine of pi over 3?
It's right 3 over 2.
Right, so that's right 3 over 4. Sine of 2 pi over 3.
Still right 3 over 2.
Still right 3 over 2 because all students, right? That would be 2 pi over 3 and minus pi. So this is, I can think of this as 2 over 2. So that's 2 rad 3 over 4 plus rad 3 over 4, so that's 3 rad 3 over 4 minus pi.
Yeah, that's what. Isn't it 4 red?
It's 4 rad 3. The 4 is on the top. Which means that's
9 rad 3 over 2.
think of this as 2 over 2, so that's 9 rad 3 over 2, and that should be positive. It's a nice problem for a class. Huh?
I'm still not getting how do you graph that?
Which
instead
one?
Of, like, how do you know to graph that kind of graph instead of the other one with the petal or with the leaves?
Yeah, the heart one?
Yeah, like how did you know like to do that instead of?
Well, I follow whatever the trig function over here told us. I didn't have to know to do it ahead of time. I followed what this was telling me. I just followed what this was telling me. So when the angle is 0, I'm on the circle of radius 4.
Okay,
When the angle is pi over 2, I'm on the circle of radius 2.
okay.
When the angle is pi, I'm at the origin. When the angle is 3 pi over 2, I'm on the circle of radius 2. And when I'm at 2 pi, I'm on the circle of radius 4. So I just plot those points and I draw something going through all those points.
Oh, okay, alright.
So the point of drawing this is to figure out how to draw that. This helps you draw that. So it's not like I would know ahead of time to draw that. I drew the trig function and it dictated what I did.
Alright, thank you.
And yep, and you can draw the other line on top of this. So that was like just a constant function r equals 3, but that just means a circle of radius 3, and I cared about this area over here.
Alright, I see that, thank you.
Any other questions? Okay. So now what I want to do is move on to the other handout I gave you probably about 3 classes ago now, Conic Sections. Looks like this. Gives you a lot of info about conic sections, and most of which we're not going to use. I really, when it comes to conic sections, I really mostly care about you being able to, first of all, recognize when you're looking at a certain kind of equation and being able to sketch that equation. So that's kind of what we're going to do. This thing about foci and directrix and where the actual asymptotes are, you're probably never going to need to actually figure that out on your own. And if you ever have to actually do it, you'll just look up the equations. But I want you to build a certain intuition with conic sections, and that comes from actually knowing how to sketch them. And in general, you are going to want to remember graphing in general. Because for those of you going on to multivariable calculus, graphing is going to happen on steroids. So you have to know how to graph 2D very well, and then graphing in 3D is not going to be that bad. Whereas if you're kind of sketchy on graphing, in 2D, graphing in 3D is going to be really okay. So. And one thing that's going to be important is knowing how to graph conic sections. So, the name kind of comes from, these are the shapes that we get by slicing through a cone, which is that. So if I can slice like this, it'll trace out an ellipse. If I slice straight across, parallel to the floor, it gives us a circle. If I slice like vertically, here it traces out a parabola. So parabolas, circles, ellipse, all that kind of good stuff. Hyperbolas, if I were to slice down here, and I get this thing and another part down here, that's a hyperbola. So all of the shapes that you can get as cross sections by slicing through a cone, we call them conic sections. That's what a section is. We actually spoke about sections briefly. We want to learn how to graph all of these guys. So, conic sections specifically. Parabolas. Now, I'm going to go out on a limb and just assume you pretty much know everything about graphing a parabola at this point, so we're kind of going to skip this. But I do want to remind you of how to graph circles, ellipses. You may or may not have seen hyperbolas before, but in either case we're going to go over that in more specific detail. emphasis on so if you get that, that's going to be good enough. Conic sections. So let's start out with the idea of the ellipse. Now, what you should be aware of, so we skipped the first page because that's on parabolas. Ellipse would be on the second page. So, an ellipse is basically just an, should we do circles first? An ellipse is basically just an elongated circle. So it's either stretched vertically or stretched horizontally. There are hyperbolas that are stretched along some sort of diagonal, but we won't really cover those. There's a thing at the back that talks about that, about rotation of axes. Basically, if you have something stretching along the diagonal, you apply some sort of transformation to turn the entire xy plane around so that it's vertical or horizontal, and it's easier to deal with. We're also not going to care about that. So just your regular ellipse, which will have this form, is the one we care about. So you can have, so x minus h squared over b squared minus y minus k squared over a squared equals 1. So this is a guy that is plus. And here I'm thinking of the a is the larger one. So basically, the guy who has the larger thing in his denominator, it is stretched more along that axis. So overall, what you should notice is that an ellipse that would look like this, kind of, and I'm going to tell you specifically how to actually get that sketch, versus if you have the x minus h squared over a squared plus the y minus k squared over b squared equals 1, and your a is the larger number, this one is going to stretch longer in the x direction. Okay. Now the center is going to be h comma k, which here I drew it to be at the origin, but it doesn't have to be at the origin. Now there are things called foci here, but you don't need to know about what those are. Technically, it's how another way to get an ellipse is to actually fix a string at 2 points, and so you can have a string attaching 2 points. What you do is you stick a pencil or something and make it taut, so right, so there's like something here holding it, and then you pretty much keeping it taut go all the way around, and that will actually trace out an ellipse. When it comes to a circle, you kind of have a string just hanging off here, and then you make it taut, and then you trace all the way around that 1 point. So the center is like an ellipse with one focus, but ellipse can have 2 foci. Don't care about how to actually find those. What you do want to know is this general form. Once you can write it in this form, it will tell you that this is an ellipse with center h comma k that stretches in the y direction because the a is larger. This is an ellipse with center h comma k that stretches in the x direction because the a is larger. Okay. That's the first thing I want you to recognize. Second thing I want you to be aware of is that sometimes you might get an ellipse in a different form, like it's expanded and scattered. What you need to do is group everything, usually complete the square, get it in that form. Once you recognize it's in that form, then you can actually sketch it and talk about the ellipse. There is another one called the hyperbola, and should I talk about the ellipse a little bit more? So let's just give a random example here before we get to the actual examples. Example. Suppose I have an ellipse that looks like this, x minus, don't want to overlap here. So let's make it look different. Let's say x minus 3 squared plus y plus 1 squared. Let's put this one over 4, let's put that one over 9 equals 1. How would you actually go about sketching? Okay. So let's say you're given some equation, you can actually write it like this, which we'll do an example where you actually have to do that, but you had to sketch this. So first, note, center is, what's the center of this?
3, -1.
3, -1. So the first step is you're going to plot the center. So on a graph an ellipse, you're going to start at the center. So So 3, -1. So that's your center here. Okay. Now here's what you're going to do from the center. You are going to look at the square root of these guys because you're going to think of the 4 as 2 squared. You're going to think of the 9 as 3 squared. Now the base here, 2 and 3, that tells you how far you move in the x and y direction respectively. So this is saying in the x direction you need to move to the left and right from the center by 2 units. So you're going to go to the left by 2 units and you're going to go to the right by 2 units. Notice that this will bring you to 1 on the x-axis, while this one will bring you to 5 on the x-axis. Okay. Similarly, this one, let's put this in a different color. The 9, I can think of that as 3 squared. What that means is from the center in the y direction, I'm going to move 3 units up. So that's going to bring us to, from -1, 3 units up, that's going to be 2 on the y, and then 3 units down. So that's going to be -4 on the y. Now what that actually does for you is that gives you a box. This gives you the boundaries. So if you kind of you can imagine that those are the boundaries of your ellipse, and you're pretty much going to touch where the blue and the green lines touch the boundary. So your ellipse will pass through this point, it'll pass through that point, it'll pass through that point, and it'll pass through that point. And then you just sketch it. That's the ellipse. Right? Create that box. So you first plot the center. Second, so for x minus h squared over a squared, I'm just putting in random numbers here, y minus k squared over b squared, move a units to left and right of center, move b units up and down from center. Create a box. And step 3. The ellipse passes through where the center lines intersect. intersect the box. So here you don't even have to remember which way is it going to stretch. You just fix yourself on the center, move to the left and right by whatever is under the square root of this denominator here, or just make sure it's right, that you're moving by the base when it's written as a square, and you move left and right in the x direction, move up and down in the y direction. This creates a box, and your ellipse is going to be stuck inside that box. It's going to be inscribed inside the box. So that is how you draw an ellipse. The other kind of conic section we want to talk about is called a hyperbola. So, general form for this one is say x minus h squared over a squared minus y minus k squared over b squared. So, when you have a minus sign instead of a plus sign, you get a totally different kind of shape. This one is an east-west opening. So, the center here, which doesn't necessarily have to be the origin, but just as an illustration. And then it'll move out here some, and it will go to the left and the right. It'll open, and it will keep getting wider and wider. And also from here, it'll open, keep getting wider and wider. So when the x is positive, it will open to the left and to the right. Versus if the y is the positive one, y minus k squared over a squared minus x minus h squared over b squared equals 1. This one will open up and down. Center h comma k. Now, here's how you would graph something like this. Maybe let's use a very similar one to what I did here. What do we have? Example. If we had x minus 3 squared over 4 minus, so I'm just going to tweak the previous example, y plus 1 squared over 9 equals 1. How do you go about graphing the hyperbola? Again, you are going to first recognize it's a hyperbola because of the minus sign. The 4, you're going to think of as 2 squared. I wrote that in green last time, just changing it up. 9, think of as 3 squared. And once again, you are going to find the center. So, 3 comma minus 1 is the center. And yet again, you are going to move to the left and the right by the 2 in the x direction. So it's going to move over, that moves over to 1 because that's 2 units from the 3. Moves over to 5, that's 2 units from the 3. Then we're going to go up and down. 3 units up, so that's going to bring us to 2. 3 units down, that's going to bring us to minus 4. And you once again create a box. You have to make the sound while drawing it, because you might lose points. You might, you have to stay focused and concentrate, because otherwise you might, yeah. Now the hyperbola has one additional thing. It has asymptotes. It turns out that these guys aren't just expanding willy-nilly, they're actually approaching lines as they go out. And how you actually get those lines is going to be the diagonals of this box that you just created. So you're going to imagine that there is a line going through the corners and the center and continuing to go forever. Same thing here. You're going to imagine that there's a line going through the corners and the center and continuing to go forever. It turns out now, when your x is positive, it will go to the sides and get closer to those lines. Whereas when your y is positive, it will go to the up and down and approach those lines. So you would start, this one opens in the x direction, so it will start here and it will open that way, and then approach these lines as it goes off to infinity, and open that way, and approach those lines as it goes off to infinity. Same thing here. And so this will just open like that. So that's how you use sketch and ellipse. Hyperbola. And yes, for the most part, I think people would know how to graph a circle. So this is when you have x minus 8 squared plus y minus k squared equals r squared. It's kind of like you have an ellipse, but the a and the b are the same number, which we will call r, and you can multiply through by r squared to get this form, which means both it's stretched equally in the horizontal and the vertical direction, so you get something that's circular instead of elongated. That, again, should be pretty clear how to sketch. So the center is going to be somewhere like here. You're going to just move by r in all directions. And then you just connect the dots. Circle I think we're okay with, but sometimes people forget how to draw hyperbola, so I just want to make sure to remind you of that. So the sketching shouldn't be too bad. You may need some calculations beforehand though, because you might not be given it in this form. What you want to do is put it in that form, recognize which one of these conic sections it is. Am I looking at a parabola? Am I looking at a circle? Am I looking at a hyperbola? Am I looking at an ellipse? And the form is going to tell you what you're looking at. Once you know what you're looking at, if I ask you to sketch it, you should know how to sketch it. So for the ellipse and the hyperbola, you have to set up this box thing. The hyperbola has asymptotes that will branch off to, the ellipse does not, and etc. Now, before I ask if there are any questions, I would like you guys to try them to figure out if you have any questions. So what I would like you to do from the handout, do problems 2, 3, and 4. And I put the answers there. Wow, I was very generous at the time I typed this. Anyway, do it that, so now you know what answer you should get once you actually go through the calculations here. But also sketch it. So try problems 2, 3, and 4. And that's actually it. That's all I care about for this section. Or maybe just to go quicker, we'll split up again in groups. He's not about it. It's 3 people. Some people do 2, some people do 3, some people do 4. Okay, well, let's get through some of these. So, Conic Sections handout. Problem 2. So pretty much identify and sketch the conic section. 9x squared plus 16y squared minus 18x plus 64y equals 71. Okay, what do we do?
You can complete the square for the x's and y's. So first we could factor out a 9 for the x's, and then in parentheses do x squared minus 2x, and then
So that's that.
and then plus 1. And then you'll complete the square, so you do 9 times x minus 1 squared plus, or then I just subtracted from like the other side. Or I added it to the other side of the equation, like where the 71
Or what
is.
did you add to the other side?
9,
Okay, so don't forget to do that.
yeah.
So yes, but let me just write it out so that
Okay.
you know that we're not forgetting to do that. So yes, this is gonna be 9 times x minus 1 plus 16 times y minus 2 squared equals 71 plus 9
Plus 64.
plus 64. Okay, which was what?
144.
144?
Yeah.
Okay,
And then you can divide by 144.
divide by 144, and what would I get?
That would be over 16. And then the y minus 2 squared is over 9.
Where 9 equals 1. So that's your equation here. So identify, well, that's an ellipse. How do I know it's an ellipse? There's a plus sign between the squares and the denominators are of different magnitudes. So I know it's an ellipse. The center is 1, 2. It is elongated
I
horizontally.
think it's supposed to be a plus 2 squared actually, because we had negative.
Plus 2 squared, where is that?
Like it should be y plus 2 squared, not y minus 2 squared.
You wrote plus.
Yeah, it's a plus 4y.
So the center is 1 comma minus 2. That's plus 64. Okay, so yeah, so that's an ellipse. It has the right form. So now we are going to sketch it. So, how did you sketch?
We did the center first at 1, negative 2. And then the distance that you would move in on the x-axis is 4. And the distance you move on the y is 3.
Okay, so on the x, you move 4 units left and right, so that would bring you up to 5. 4 units here, that would bring you up to minus 3. And the y,
Move up and down.
let's exaggerate that a little bit more. Go all the way up to the board here. Call that 5. Call this minus 3. And the y, we would go up and down by 3 units, so that will go up to 1 and down to minus 5. So then I would be able to create that box. Okay, and our ellipse just lives inside of that box. So it's here, 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 and here. Something like that. Okay. We'll do problems 3 and 4 next time, and we'll start a whole new kind of topic. We'll talk about sequences. This is a preliminary to series, which is, it's gonna be awesome, but it's also going to feel very different from what we've been doing. So I'll see you on Thursday. Well, I'll see you tomorrow, but on Thursday we'll continue that.